Recorded is rolling. It is Monday, March 30th. Oh, yeah. Welcome back from spring break. Hope you guys had a good spring break. So, the week before spring break, we were doing some optics. You guys remember ray diagrams? You guys remember magnifying glass? We were saying, oh, how does something magnify? We're looking at diagrams for that. Yeah, you guys will see that again today. You guys will see a review. And then yeah, I want to do more with electromagnetic spectrum, and that's what EM stands for, by the way, electromagnetic, right, electromagnetic spectrum, and optics. Right, so I got some slides for you guys. Tomorrow we'll do a Kahoot. I gave you guys a page. On one side are four mirror puzzles. Actually, we're gonna do these pretty soon before I even get these slides. On the back side are the questions that are gonna show up on the Kahoot tomorrow. Okay, and then now Wednesday's gonna be kind of a weird day. So yeah, is anybody in 10th grade? Who's in 10th grade in this class? Who's in 10th grade? 10th grade. A few of you guys, a few. So if you're in 10th grade, there's best testing going on. I think you have to write some essays, I think, something like that. So that's first three periods. Now, guys, if you have any questions about where you're supposed to be testing, do you think on Google Classroom I posted an Excel file that shows where everybody's testing?
Yeah.
Yeah, right. And if you're not testing, it's possible one of your first two classes is going to be relocated. So there's a different tab in that same Excel file that tells you where to relocate if you have to get, right? So any questions about Wednesday? Wednesday, a little weird day? Okay. Now, my own class, I'm going to be proctoring this classroom, but only the first two classes. So by the time seventh period rolls around, I'll see you guys. But these are my own relocations for what matters. Like that. Um, right. And you guys, I want to get you guys a EM spectrum and optics quiz. It's going to cover some material that we did right before spring break and some material covered today and some tomorrow. So yeah, kind of a combination of all those type questions. I'll let you guys do an open teammates. You guys can help each other out, and I think you guys will do good there. And then I want to finish this week with Venom's wheels. So, how do you guys create one of these? Actually, no, since I got this one working, you guys see all these colors here? What happens if you put all the colors together? What color do you get?
Black.
Well, it depends. There's two ways to add colors. I heard white and I heard black. Let's see this. Ooh. No, there's a certain frame rate on this camera, so this works better in real life than with the camera, but it kind of works here. Can you guys see what color it sort of wants to flash to if it spins real fast?
White.
Yeah, it is tending towards white, and it works, like I said, like better in front of your face than it does like going through some camera with the frame rate. Yeah, but okay, it was white for a little bit there. Yeah. So we'll take a look at that. And then what would cause it to turn black? Or how does it that you mix paint colors together and they get dark, right? So we look at that. And then no school Friday. So there we go. We got a nice short week here. Okay. All right, so let's look at these mirror puzzles, mirrors. You guys remember doing this ray diagrams and I have a looks like actually these are plane mirrors going on. Plane mirrors. Okay. So got this lady standing 1 meter in front of a mirror and say she wants to look at this flower on top of her head, but she can't see it directly in this dresser mirror. Instead, she can see the reflection of the reflection in this handheld mirror. You see that? And she's looking at the reflection of the flower. Okay, and this handheld mirror is a half a meter behind the flower, behind her head. Okay? So how far in the back of the dresser mirror does she see the image of the flower? So starting from the plane of the dresser mirror and going backwards, how far away is that reflection? So go ahead, take a minute. You guys can talk with each other and write a number right here and see how many guys got the correct value. How many meters behind the plane of the dresser mirror does it appear like is the reflection of that flower, which is really a reflection of a reflection? How far into that?
Big fence there. I think it's all. Mr. Fletcher,
Wait, Mr. Griffin,
Yeah.
does it matter? Go right?
Nah. Just to get you guys thinking. Yeah. Welcome back to school. Get you guys. Okay.
No.
He's back into thinking how things work. How does the universe work? That's physics. Who thinks they know the answer? Came up with a number. All right, I'll narrow it down. Let's do A, B, C, D. A, B, C, D. It's either a 1 meter in the back, 1.5 meters, 2 meters, 2.5 meters. Well, it's got to be one of those. Yeah, so,
Yeah.
All right, guys ready to do show hands? Show hands. Okay. Who says A? Who says A? Who says B? Who says C? Yeah, I said C. Yeah, all right, got some letters. I'm gonna go with 2 meters, 2.0 meters, right? And I'll show you guys why. Right, so why is it 2 meters? Right. Well, the initial reflection, let's just do the handheld mirror. See, like, where would the reflection be in a handheld? Okay. Wouldn't this flower show up as a half a meter behind the handheld? So the 1/2 a meter that way. Would that be true? That's okay, right? Half meter, half meter. Right. Now she's looking in this dresser mirror. She's seeing this reflection of a reflection. Ooh. So she's really trying to see this reflection back here. She can't see the flower directly, but she can see the reflection of the reflection. Okay. So this whole distance right here is 2 meters. Therefore, the reflection of the reflection also shows up as 2.0 meters the other way, and she can see it. Right. And that's how far and back it looks up. Right. Okay. Which I guess if you also add this mirror, this distance from her face to the dresser mirror, it could be like 3 meters from her face. Well, it looks like the flower is 3 meters away from her eyeballs. All right. Ooh, this next one's a little trickier. In order that you're able to see a full length view of yourself, what's the minimum size of a plane mirror? Right. Let's say this guy is 6 feet tall. Right. You guys that he'd be 6 feet tall. Right. Now, if he stands in front of a dresser mirror that's also 6 feet tall, is he going to be able to see his entire reflection? Yeah, he should. Right? No, unless you like shift the mirror like way up or way down, but if it's centered also on him, then he should be able to see his whole reflection, right? That'd be true. What about this? Is what if this mirror was only 5 feet tall? Would he still be able to see his entire reflection? Huh. Right. Go ahead, take a minute. And what do you think? Oh, well, actually, you have multiple choice on this. Okay? So it's got to be one of these. Okay? Is the minimum size of the mirror a quarter of this guy's height, half his height, 3/4 of his height, his full height? Or does it depend on how far away he's standing? Maybe if he stands real close or real far away, maybe the answer changes. Possibly. Huh. You guys think about that. What do you guys think?
Where's that? What about- oh,
It depends on your distance. Yeah, that's my thought. That's fair.
But before I say show of hands, I'll help you guys out a little bit. I'm gonna knock out one of the answer choices. Have you guys ever stood in front of a glass surface? Maybe, or I know I've been to an airport terminal and they have these glass walls, and maybe it's nighttime outside, so it's really reflected. Right, so you're inside a bright room. It's nighttime outside. You can see your reflection really well, right? And if you stand really close to that glassy wall, you see your reflection. If you look at where's the top of your head and where's the bottom of your feet, it's supposed to make a like a mark, or it could be an imaginary mark, maybe up there, like a little smudge. Okay? And you start backing up away from that wall. Okay. Turns out that where the top of your head is and where your shoes are and your reflection is the exact same locations. Okay. You can try that out. Next time you're in front of a mirrored surface where you can see your entire reflection. Okay. What that means is, which one of these choices did I just eliminate? Yeah, so we just eliminated option E. It can't be that one. Okay. Turns out it doesn't depend on your distance. Right? Whether you're standing 2 feet from the mirror or 20 feet away from the mirror, you need the same amount of mirror to see yourself. Now the question is how much? Check this out here. This guy is playing here. See how tall I just make this guy. Looks like 6 centimeters. That matches with my 6 foot example before. Okay. My stick figure I just randomly drew is exactly 6 centimeters tall. This guy's 6 centimeters. 6.0 centimeters. All right, you guys ready? You guys ready before I draw the solution? Let's see, show of hands. Show of hands. How many guys said A? How many guys said B? Who says C? Who says D? Ooh. Right. Who said B again? Who said B? There's my winner right there. Yeah, winner. Now, why is it only half? So I'm making the claim that this guy is 6 feet tall. He only needs 3 feet of mirror. Now the catches needs to be positioned exactly in a certain location. Okay. But if he looks at the top of his head and bottom of his feet, makes a smudge there and a smudge there, it should be only a 3 foot gap. All right, let's see if that works. Okay. So here's my object right here. He's 6 foot tall. Here's my mirror. It's a plane mirror, just a regular flat mirror. Okay. Now, how far away did I put this guy from the plane? Let's say I put him about 5.5 centimeters up there. So you guys remember from before spring break and probably just life in general, the image is going to show up 5.5 centimeters on the other side. Make him also 6 centimeters tall. Right here. This is pretty dang close. This should get the idea across. Okay. So here's the image. Okay. Oh, guys, would you call this a virtual image or a real image? What would you call this?
Virtual.
Virtual, yeah. How'd you know it's virtual?
There.
Yeah, because it appears to be on the opposite side of the mirror. Right? That's in contrast to, you guys remember this little UFO pig? If you're, like standing, there's show right there. You see, it looks like it's right there. I can reach out and grab it. Yeah, can't reach it there. That's a real image. But this is virtual because it looks like on the opposite side. Right? Now let's follow a few rays here. So here's about his eyeballs right here. He's looking at right here. Okay. So he looks up and sees the top of his head. Now this line is almost parallel to the ground, but maybe it bounces a little bit, pointing like that. Okay. And it looks like it came from this direction. And this light ray, I guess, would extrapolate out that way. Okay. So that could be true. Great. Could that be one ray of light? Going like that, like almost parallel to the ground. Okay. Then he looks down at his shoes in the reflection. He says, well, it looks like my shoes are kind of off that way. It looks like there's a light ray coming from that way, which would indicate my shoes or my feet. Okay. But really that light ray bounces boing back in this direction. Something like that. Right. And then you could of course extrapolate into the mirror world that look like that. Okay. So here's a couple rays of light, boing entering his eyeball. And he says, oh, it looks like there's top of my head and bottom of my feet. It's okay. Okay. Now, here, do you guys see the amount of mirror he actually needs to see himself? It goes from here to here. It's just this bit right here. This bit right here. Okay. All this, irrelevant. This little bit right here, irrelevant. He just needs this bit. Okay. Now, I mentioned before, I said this guy is 6 centimeters tall. So how tall do you think this bit of mirror is right here? I think it's 3 centimeters. Let's check it out. It is! It's 3.0 centimeters. This right here is, from here to here, is 3.0 centimeters. Sure is. Just like that. Okay? Here's that. Okay. Again, it doesn't matter where I position him relative to the mirror. This will always come out to 3 centimeters. And if I change its height, then the amount of mirror he needs is always going to be half of its height. Okay? All right. Ooh, which actually leads really nice to this next question. Let's say you're holding one of these cosmetic mirrors out here for a visual. Okay, so you're holding this cosmetic mirror, you're trying to see your face. She says, either the mirror is too small or my face is too big, or I need to see more of my face. How do I see more of my face? Should she hold the mirror closer, further away? Or do A and B both fail and she just needs a bigger mirror?
Well, wait, she wants to see more from her.
Yeah, she wants to see more of her face. How does she do it?
Move your eyes.
When
you see your whole body.
so I try that. Let's see, wait. Oh, sorry, here's the flat side. Try flat side. Yeah. Alright, show hands. Who says she should hold the mirror closer? Who says closer? Who says further away? You know what? I'm passing that handheld around. You try it. What do you actually see? It's not A and it's not B. Okay, you just need a bigger mirror. Okay. Guys, it actually goes back to this question. It links to a similar principle. Okay. You guys remember this guy right here? He can see his whole self. But it doesn't matter if he's standing close or far away from the mirror. He needs the same amount of mirror to see his entire reflection, doesn't he? So if you replace your entire self with just your face, it's the same principle. Right? Same principle? Yeah. Because if you hold it, now make sure you're not looking at the concave side. Make sure you're looking at the flat side, right? The flat side. Okay. Yeah, you can hold the mirror closer or further away. You should see the same amount of your face regardless. So the answer is C. Needs a bigger mirror. Okay. You guys good on these so far? Okay. How about this last one? We got a reflection. Well, great. Just taking a photograph of her friend on a bridge here. And we got option A, option B. Which one of these more accurately represents the picture that she took. And what do you guys think, A or B? Does anybody say A? Does anybody say B? Why is B?
That has the shadows.
Yeah, you can see the underside of the bridge here. You guys see this one has the underside of the bridge? Okay. The option A, just mirrored straight down, but option B, yeah, you can see the reflection on the underside of the bridge. All right. So got some mirror puzzles. Go ahead and hold on to those. Those are just for you guys. All right, and all right, let's do some slides here. Hey guys, you guys know I'm going to give you guys a team quiz in a few days, and some of the questions might involve those mirrors. Some of the questions might be stuff we did before the break a bit. In that case, there'll be a review right here. Some questions come off these slides. And so electromagnetic spectrum. Ooh, guys, what does C stand for in physics? Yeah, speed of light, speed of light. Hey, actually, does this look familiar in general? Speed equals what times what? How do you read that? Yeah, lambda is wavelength, F is frequency, so wavelength times frequency. Okay. Some textbooks use a Greek letter, I think it's nu, it's kind of like a curly V or something for frequency. I just use F, so yeah. Okay. So this is a wave, and this is a wave, the classical wave equation that you guys have used before, but it's special for this category of waves called electromagnetic waves. Okay? And actually, what your eyes can detect is only one tiny, tiny portion of a much larger phenomenon. You guys see all those colors here from red to violet? Okay? Now, the wavelengths that are associated with those, well, they're right here, 750 nanometers to 380 nanometers. Okay? If it's an electromagnetic wave, that's what your eyes can detect, and your brain turns into color. It's somewhere on that color spectrum. Okay? So if you back up, there's a much larger phenomenon going here. So if you stretch out the wave a little longer, all right, let's say you start with green and then make it longer, now it's yellow. Now you make it longer, now it's red. Guys, if you keep stretching out the red, then it turns into what? Well, yeah, it becomes invisible. So it's not a color, but it's what do we got right here? Infrared, infrared. Ah, like beyond red, infrared. Right? And if you keep stretching that out, that becomes what? Microwave. Ooh, you guys have a microwave oven? Those waves are usually a few centimeters long. It might be like 10 centimeters plus or minus a few centimeters. Okay? And then the width of your box is going to be some multiple of your microwave box. It's going to be some multiple of that, so that they'll resonate. So the standing wave. Okay? And if you keep stretching that out, you can eventually get to what? Radio waves. Right? Did I have you guys calculate? I forget. Did I have you guys calculate what's the wavelength of an FM wave that's coming in?
I think you talked about it.
Here, let's go ahead and do that calculation. Let's do that. We flip over here. Okay. So let's say you got, let's say you tune into 96.5 FM. Okay, that's an FM station, but really 96.5 has units attached to it. Guys, what's the units on 96.5? Megahertz. Megahertz. Okay. And what is this mega actually right here? That's 10 to the power of what? 6 for a million? Okay. Like 1 billion. 1 million. We got right now. I was just showing you guys speed equals wavelength times frequency. That's a special speed. It's the speed of light. Really, it's all the speed of all electromagnetic waves, and really anything that's massless has to be moving through space at 3.0 times 10 to the what? 8 meters per second. Okay. So at 300 million meters per second. Okay. In place of lambda. Well, actually, that's what we're solving for. We want to find what's the wavelength of this. Right? Because I could have a radio right here and I could tune into the station and get music in. Right? But how long are those waves? Okay. And then frequency, I'm going to put 96.5 million. And that's hertz, of course. Okay. So, hey, can I just take this and divide by this? Now, let's do that. Let's do 3 times 10 to the 8. Put that in parentheses. Divide by 96.5 million. I'm looking at, yeah, that looks about right. Okay. Approximately 3.1, I'll round it a little bit, meters. Okay. About 3 meters long. Guys, all those FM stations that you can tune into in your car, so between about 88 to 108 megahertz, okay. They have wavelengths that are approximately 3 meters long. Yeah, so a little shorter, a little longer. You said? Okay. And the fact that you could tune into that in this room, guys, in this room, are those radio waves passing through the walls and through the ceiling right now? Yeah, there's some transmission tower many miles away that's pumping out those waves. And if you had the radio you could tune into them because those waves are traveling right through the wall. Hang on a minute. Let's go back here. I thought these were all the same phenomenon. What about these light waves? Can these light waves travel through the wall? Can you see next door? Do you know what they're learning next door over here? I have no idea. Huh. Right. Unless the wall was made out of glass, right? Then the visible light could go through. Right. Hold to that idea. When we cover quantum mechanics, we'll cover why right now I just want to plant the question, the idea like why is it that some parts of the spectrum can maybe travel through certain materials like the wall for radio waves, but light doesn't. Okay. What about that glass there? Why can visible light travel through the glass? Okay. But what about those other parts of the spectrum? Do you think what about infrared? And what about the ultraviolet? Do you think those travel through glass? Hmm. Let's look at all right, yeah, let's go back to the color spectrum. Okay, so let's start with green, and let's make the frequency higher and the wavelength shorter. Now we got blue, then shorter. Now we're to violet. And guys, if you have a violet color and you make the wavelength even shorter, now you can't see it anymore. Now it turns into what? Ultraviolet. And if you make that shorter, that turns into what? X-ray. And then go even shorter, that turns into what? Gamma. Right, so we have a whole spectrum there. Right. Ooh, color mixing. So, if you could zoom in microscopic on your phone, say you had an ant crawling around on your phone, and your ant can see. Do you guys think there are just certain pixels that lighten on your phone? Right. Really, we're talking about like subpixels. I don't know if that's a term for it. Right? But how many different colors are there to light up on your phone? Yeah, it turns out there's only three. Guys, your phone only has three colors on it. And what are those three colors? Yeah, red, blue, and green right here. RGB standard, red, green, and blue. Right? Wait a minute. How does your phone make a white background? How do you get white?
Putting them all together.
Yeah, you light them all up at the same time. How do you get yellow? Yeah, it turns out if you lighted the green and the red at the same time. Now, if you were like an ant crawling around, you might see, oh, there's some green specks there and there's some red specks there. But if you back up from like human scale, it just looks like yellow. Right? Actually, that yellow right there, coming from that projector, it's not really yellow. It's just a bunch of red and green lit up. That's all it is. It's just red and green. Right? And these other colors too, right? But what about this? Let's switch over let's get away from your phone screen. Let's look at, how about, you guys have a color ink printer at home? Color ink? Okay. And what three color cartridges do you put in?
Yellow,
Yeah, yellow, magenta, and cyan. Right, now this works differently. Okay. Now, can you get black out? Suppose you run out of actual black ink. Can you get black from your color printer?
Yeah.
Yeah, how do you get that? Hey, mix them all together. Right, so we got two different kinds of mixing going on. This additive mixing on the left, this is what Isaac Newton figured out. He realized you could take white light and put it through a prism and it refracts a little differently. You can split and get different colors. So you can put the colors back together and get white light. That's additive mixing. Right? It's your phone screen. Right? But if you're working with paint or ink, right, then the more colors you mix, it actually subtracts out each band of color. So the more different colors you mix, it subtracts light, right, until you end up with black. Right? Black is the absence of reflection of light. Right? Okay, so different kind of color mixing going on. Right. Ooh, this one's fun. Okay, so stare at the middle for about 30 seconds, and then I'll flip the screen, but you have to stare at it for a while. This is called retinal fatigue. So you guys have cones in your eyes. You should have three different colored nutrition cones, unless you're colorblind to one of them. Okay? And then the three cones, there's one for red, one for green, one for blue. Okay? That's why it works, right? But right now, your cones are getting used to the colors that are already there. So when I flip the image, it's going to flip to the screen. Your eyes will perceive the opposite. Kind of like if you walk into a bakery, you smell bread, but after an hour you don't smell it anymore because you get used to your surroundings. Right? Then you walk outside and it's like, whoa, I can smell some fresh air that I didn't even notice. All right, you guys ready? Right, now stare at that for a minute. Stare. Now do you guys see three different color apples? What colors do you see from left to right? That sounds right. Yeah, I think one of them was yellow, one was red, one was green.
Yeah.
I forget the order myself. But you guys have seen it. You guys seen that? Here, let's do that one more time. All right. So stare at the middle. Maybe you got it first time, maybe you did. If there are two that look identical, then might want to get tested for color blindness. There could be. I think I forget how that works. It's like isn't like overwhelmingly like guys get color blindness if anybody does it. I think girls almost never get it. Okay, yeah, something about Y chromosome or something.
It's a recessive trait.
Okay.
So like,
Yeah.
Yeah, they're both.
Yellow.
Red in the middle. Yellow, red, like a little bit was yellow.
Huh.
Yeah, it's like
All right.
mom. So mom needs to be
Yeah.
bigger,
Okay.
colorblind. So mom needs to be carrier of it, and your dad has to be colorblind too.
Oh, okay. And so girls can be colorblind. It's just really, really
So
rare.
excessive, yeah.
Yeah. All right. All right. Yeah. So here's our Project Thursday. Use that to round out the week. Okay. Here's what you guys did before. All right. All right. Let's talk about how bright can something be. Let's say you go to the store, you buy a bicycle light, and it wants to quantify how bright is the light. You might have a dim light, you might have a bright light. Okay. So here's three different perspectives on it, and they're all a little bit different. Okay. So do you guys remember way back at the beginning of this class, like first week or two of this class, we were talking about units that you can measure in. It's like, okay, I can measure mass in kilograms. I can measure time in seconds. I can measure a distance in meters. So those are the first three units. Okay. And there are a few more. So how do you measure how bright is something? So typically they'll say, okay, yeah, either lumens or candelas. You could really start with either one of these. Usually they list candelas. Lumens, I think, would be a better choice though. Okay? And usually bicycle lights are listed in lumens. Right? But here's the difference. Lumens is just how bright is it overall. So if you just had a single point of light that was sending light in all directions, right? But you could do this. Guys, isn't it true on your bike light? There's normally like a mirror on one side. And so the light doesn't actually pass the mirror, right? But it does get reflected. So does the intensity therefore increase? The intensity increases the side it's all being reflected towards? Yeah, same thing with a flashlight. If you look at a flashlight, do you have one here? Or maybe, right, anyway. So yeah, no, this putting a mirror here doesn't actually change the flux, doesn't actually change the overall flux in lumens, okay? But it does increase the intensity in candelas. And what is one candela? It could be 1 lumen per steradian. You guys see this SR right here, steradian? You know, this is like an angle in 3 dimensions. So can you guys imagine not a circle, but a sphere? Here, I'll draw this out, sort of. Draw this out. Okay, this is kind of a tricky concept. Okay. But you guys know on a circle, like a flat 2D circle, if you go from here to about here, if this is R and this distance here is also R, isn't this theta equal to 1 radian? Isn't that true? 1 radian? Right. Right. But can you think in 3 dimensions? So this is a circle, yeah, but this is a sphere. Ooh, a sphere. So what if I had some distance R, like in 3 dimensions? Yeah, think in 3 dimensions. Okay. And I sweep that out and make a circle right here. Make like a cone shape. Yes, yeah, that cone shape. Right, so like that. Where this area right here is, I think it works out to R squared. Like if this is R is 1 meter, it could be 1 square meter. Okay. If I remember right, I think that's what 1 steradian is. But it's like an angle, but in 3 dimensions. Okay, that's it. All right, so now we have a way to think about angles in 3 dimensions. Okay, so there you go. 1 candela is 1 lumen per steradian. Now you can use a mirror to send light in one way. Right? All right, finally, illuminance. So, guys, what if you back up further and further away? Does the light appear to be dimmer?
Yeah.
Yeah, because your eye is not catching as much light per area. Okay. And that's an illuminance question. The first two have nothing to do with that, but the last one does. Okay. So here's another perspective on the same idea. Okay. So let's say the luminous flux is 4 pi lumens. Oh, I meant to mention before, is what's the surface area of a sphere in terms of its radius? Okay, yeah, there's a pi in there. Yeah, the surface area equals 4 pi r squared. Okay, so what if this r? If this r is 1 meter, 1 meter being squared and then times 4 pi, is it? Okay. Which helps make this make sense right here. Okay. So if you have 4 pi lumens of luminous flux, okay, and then you just roped off 1 steradian, you would get 1 candela of intensity. Okay, so okay. This is assuming it's all directions, yeah. Right. But what if you back further away? I'm 1 meter away. Now I'm going to go 2 meters away. Now 3 meters away. Okay. Notice that the flux or the intensity, none of that changes. Right. What does change is the illuminance. You guys see per square meter? You see that? Right. So if you, okay, how about this? If you back up 3 times further away, I think this is a quiz question. Or there's a quiz question that's very similar to this. Right. So we're just covering it here. Okay. We're just covering it here. It's going to show up on the quiz in a few days. Okay. If you back up 3 times further away, what happens to the illuminance? 1/9. Do you see that? It's like an inverse square law. You see that? Okay. But the flux and the intensity don't actually change. Okay. But the illuminance does. Okay. Right. Ooh, here's a little bit of astronomy. So if you look up in the sky, you see a star, it's some amount of brightness. what does that have to do with anything? Right. Well, the further away it is, it'll appear dimmer. You guys know that from illuminance. Right? But how bright the star actually is, say at some set distance, also has to do with how large it is, its radius, and also its temperature. Right. So this is equation you can come up with that involves this Stefan-Boltzmann constant, which looks like this. Right. Anyway, you could figure out if you know some things about a star, like how bright it is, you can figure out either how far away it is, what its temperature is, or how big it is.
What's that circle thing in front of the T?
This right here. So that's Greek letter sigma, and in this context, it stands for Stefan-Boltzmann constant, and it's this crazy number right here.
Oh, I didn't see that.
Right.
All right.
Yeah. Here.
Like, what's
Um,
that?
Here's one thing you can do with this is spectral line. Now here's spectral lines for the first 8 elements. Have you guys ever read a science article? It's like, oh, scientists discovered some exoplanet that's crazy far away from us, and we think it has water vapor in its atmosphere. Like, how would they possibly know that? Right? Like, you know that from spectrometry. So there are waves of light that pass through the atmosphere of that planet, and then they say, hey, we have hydrogen and oxygen in a 2-to-1 ratio, so it's probably water on that planet. Okay. Ooh, did you guys remember Doppler effect? You guys remember some of those puzzles? The car goes by and you're standing on the sidewalk. Meow, meow. So there's a similar effect with light, but the equation looks a little different. And the reason the equation looks a little different is because light works differently than sound. So sound needs a medium to travel through, and that medium itself might be in motion. Maybe there's some wind or something for the Doppler effect, right? But when we get to the theory of relativity, which we'll do in a few weeks in this class, light doesn't actually need a medium to travel through. And that was a really, really weird concept for people to wrap their minds around. Actually, Albert Einstein first figured that out. And as a consequence, this Doppler equation looks a little different than it does for sound. Okay? So you can say, what's the observed frequency or observed wavelength? I have both equations listed here. Here's the speed of light, precisely. Okay? Guys, if you look up in the sky and you see there should be some color of, goes back to these spectral lines. Say if you're looking for hydrogen or oxygen or whatever, right? But what if it's shifted a little bit towards the red side? It's a little bit towards the red that it shouldn't be. What does that tell you is happening between your galaxy and that galaxy? Yeah, you're moving further apart, right? In fact, almost every galaxy relative to us is moving away from us, and the further away they are, the faster they're moving. So that helped lead to Big Bang theory was one of the but if you look at Andromeda galaxy, it's actually blue shifted. So Milky Way and Andromeda are on a collision course for that reason. So, okay. All right, let's do some review here. Do you guys remember law of reflection? This angle of incidence, angle of reflection is the same. And notice I'm measuring relative to that normal line. Here's your mirror right here, reflective surface. All right, law of reflection. If you have a curved surface, you could have an associated focal length, which is at r/2. Got that. You guys saw all this before the break, just a reminder. Right? Here's a plane mirror. Actually, we did a little bit of plane mirror earlier today. Okay. Here's a convex mirror. You guys remember that? I think you guys have all these papers back, right? You guys have all these, right? And then here's a image location. You guys remember applying that formula? Right? I'm pretty sure on the quiz coming up in a few days, this is going to be helpful. This equation. You guys remember this equation? 1 over the focal length is 1 over distance object, 1 over distance image. You guys remember that? Okay, so we did some of that in class. I'll show it. Okay. You got a concave mirror. That same equation would still apply. The same equation would still apply. Right. Here's front side of a spoon. Here's also front side of a spoon, but use back your face away from it. Okay. Hey, we just did that earlier. Right. So the minimum size of the mirror you need to see your entire self is half your height. So you guys saw that earlier. Got that. Ooh, this is fun bonus. You guys ever ridden I know a few Disney rides use this. I know Haunted Mansion is one of them that uses this. Have you guys ever been on a Disney ride and seen like some ghostly figure like run across the room, something like that? Okay. Yeah. So what you're actually seeing is a reflection of a glass pane at 45 degrees, and there's something that's hidden where you can't see it. Maybe it might be like in tracks underneath you or something. Okay. And so you're actually seeing it's called Pepper's Ghost. See that? Refraction. You guys remember anything that smells all that? Oh yeah, good.
I had a question about this.
Oh, yeah.
So if you have a mirror and then like a book in front of that, when you put like your hand, when you look in the mirror, you can see your hand. And how does that work?
If you
Like, okay, so it's a mirror.
Yeah.
And then something blocking the mirror. Then you put your hand. If you look in the mirror, you can see your hand behind the book. Yes, you can. Yes, you can.
Well, maybe if you're at an angle, like you're looking from above, right? Yeah, because then a light ray could like bounce off that direction. Yeah, yeah, yeah.
Oh,
Yeah, yeah, right, yeah, yeah, yeah. That's good. Yeah, good thing to think about there. Yeah. All right. Yeah. Okay. You guys remember Snell's law? Let's review this. Right, because this question's gonna pop up on your quiz pretty soon. You guys remember applying this? Guys, what does N stand for? It's called the what? Index of refraction. Aha, index of refraction. So for a perfect vacuum, this would be exactly one. Air, we'll call it also one. But what about for water? I think water is like 1.33. And so what's the speed of light in a vacuum compared to the speed of light inside that material? Right? So like water is like 1.33, something like that. And if you know these angles, well, if you know one of these angles, you can calculate the other if you know the index of refraction. Or if you know both angles, you can calculate the index of refraction. Say like, I don't know what material this is, right? Something like that, right? Is anybody taking forensic science? Anybody doing forensic science? Right. Yeah, this is one thing they'll do is they'll take some piece of glass, and there are different kinds of glass with different indices of refraction. They'll put it in like a special oil, like a liquid, and it'll change the temperature of the oil, which changes its own index of refraction until they match, and then it looks completely invisible, and they know, okay, well, what's the index of refraction? What kind of glass is that? You guys remember total internal reflection? I saw that. You guys did Snell's law. Here's lenses, lenses. You guys remember converging lenses? You guys did. You guys remember diverging lens? Right. You guys have all these in your ray diagrams. Right. You guys did all these before spring break. It's just a review here. You even saw this. Right. Why does the moon turn red during lunar eclipse? I think you guys saw rainbow too, right? You guys saw rainbow. You guys saw rainbow. Right. Iridescent. Yeah. You guys see that blue butterfly right there? So suppose you found a dead butterfly. Butterfly's dead. Let's say you put it in a like a bowl and take a mortar pestle and or whatever they call it, and you grind it all up. Right? Guess what happens to the color of the wings? Yeah, it goes away. It's no longer blue because it's not actually blue pigment. What it actually is it has to do with the nanostructure of the surface of the wings and the way the light reflects off creates these interference patterns. Right? So there's no actual blue pigment. Yeah, yeah. Similar idea with film iridescence, like a soap bubble, like that. Telescopes. So here's the Galileo telescope. Used a converging lens and a diverging lens, and it got an image. Right. Kepler was using converging and converging. Now the disadvantage of two converging is that the image actually flips. Right. You guys can see if you follow the rays. Right. But there's another problem with using lenses in general is that you guys remember chromatic aberration? The colors spread out a little bit differently from each other. Okay. So what's the solution again to that? To prevent the chromatic aberration, you don't use a lens. You use a what? A mirror. Aha. There's Isaac Newton's invention there. So there's your mirror telescope. Mirror telescope. Got a mirror here. All right. And then, all right. Got some images. All right. Pretty good. Pretty good there. All right.